I just want to give you a quick summary of chapter 6 and 7. It seems like there's a lot of material coming up on test 3, but what I want you to understand is there are actually only a couple of things we do in chapter 6 and a couple of things we do in chapter 7. So I know that a lot of times when you are working through the homework and you're doing 10 problems in a row that are from 6.3, it seems like the material's easy because you're doing the same thing on every problem. And what gets difficult is when you have several different types of problems thrown together on a test and you have to sort out what I do on each problem. And that's why I wanted to give you this overview of chapter 6 and 7. This handout is in Momentum. You should print it and just pause the video if you want to print it now, but we're going to talk about the different types of problems that are in each of these chapters. Section, not section, chapter 6 is the normal distribution, and really we only did two things in chapter 6. Either we were looking for a probability, a percentage, or an area when we were given a z-score or a range of z-scores. Whenever we were looking for probability, percentage, or area, we used normal CDF. That's what normal CDF gives us. It gives us an area or a probability. If we want a percentage, we can change our probability to a percentage. But on all of these problems, the most important thing is to draw your normal distribution. If your normal distribution is drawn correctly, then most likely you are going to enter the variables on the calculator correctly. So I've given 4 examples. These are really the only 4 things that can happen when you're using normal CDF. Either I give you one z-score and say what's the probability of something being less than that z-score, or this may be an x value instead of a z-score, but still I could give you something like find the probability that an individual man weighs less than 150 pounds. That's when we used inverse norm. I'm sorry, not inverse norm, normal CDF, because we're looking for a probability. And whenever we use normal CDF, we have to enter a left boundary and a right boundary. If I say what's the probability that a man weighs less than 150 pounds, I'm talking about shading all the way to the left. And when we shade it all the way to the left, we use negative 9,999 as our lower boundary. So on the calculator, I would enter normal CDF, the negative 9,999, up to whatever weight I was given and whatever mean and standard deviation I was given. Or I could have a situation where I was asked, what's the probability that an individual man weighs between maybe 150 and 180 pounds? Then I would draw my normal distribution. I would put the mean and the standard deviation in the middle. I would mark my lower boundary of 150 pounds, my upper boundary of 180 pounds, if that's what this example was. And then I'd simply enter it on the calculator as normal CDF. The left score that I was given, I'm just going to use Z sub L for that. That just means the left score, whatever it is. And then to the right score, and then the mean and the standard deviation. Or I could be asked a question like, what is the probability that a man weighed more than 200 pounds? And I'm just picking on men because they make a good example here. But the probability that a man weighs more than 200 pounds, I would draw my normal distribution with the mean in the middle. I would put 200 pounds wherever it goes in relation to the mean, and then weighs more than 200 pounds means I'd shade forever to the right. And whenever I shade forever to the right, I use 9,999 as my upper boundary. So I would enter that on the calculator as normal CDF, the z-score or x value that I gave you, up to 9,999, and then enter the mean and the standard deviation. And the only other thing that can happen is rather than having the middle or just one of the ends shaded, I could have both ends shaded. And I could give you two different scores. I could say, in the case of maybe the Celsius thermometers in section 6.2, I could say, what's the probability that a thermometer had a reading less than -1 or greater than 0.75? Well, there's two ways that you could get the area in the ends. You could find them separately. You could do normal CDF -9999 up to the left score, and then you could do normal CDF, the right score, up to +9999 and add those two areas together. But I think it would be easiest if you recognize that what I'm shading, what I'm highlighting in yellow is the complement of what was already highlighted on the ends. Then I would find the area in the middle, normal CDF, from the left z-score to the right z-score, and the mean and the standard deviation. If that's the area in the middle that's highlighted yellow, then the area on the ends is 1 minus that. And I can enter that straight left to right on the calculator, 1 minus normal CDF, the area in the middle. All right, so one thing that we did in chapter 6 was you give me a z-score or an x value, you give me a range of temperatures or heights or weights, and ask me for some area bounded by those scores, then I'm going to use normal CDF. But if you ask me for a z-score or an x value, for example, if you ask me for a weight or a temperature or a time, and you give me some probability or some percentage or area, that's when I use inverse norm. You still need to draw the picture. If I give you this diagram, or if I say, find the weight that separates the lightest 90% of men from the heaviest 10% of men, then I'm asking you for a weight. That's when you use inverse norm. And when you use inverse norm, remember you always, 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 and I'm going to write this down again for you, always enter the area to the left of the desired score, the value you're trying to find. So if I gave you some area to the left, again, I may say, the lightest 90% of the men. In that case, 90% or 0.9 would be the area to the left. That's what you would enter on the calculator. Whatever I give you for that area on the left, that's what you enter, and then the mean and the standard deviation. However, if I give you this diagram and I've told you the area to the right, then you can't use the area to the right. Inverse norm, you have to enter the area to the left. If you know that the area to the right of the score you want is alpha, how do you find the area to the left of the score you want? Well, if the area to the right of z is alpha, then the area to the left of z is 1 minus alpha, and that's what I have to enter on the calculator. Inverse norm, not alpha, but 1 minus alpha, and then the mean and the standard deviation. Those are the only two things we did in 6.2 and 6.3, and the only difference in those two sections, 6.2, we were dealing with the standard normal distribution, where the mean was 0 and the standard deviation is 1. When that's the case, I really don't even have to put them in the calculator when I use normal CDF or inverse norm. You can go ahead and enter 0, 1, but if I just close the parentheses after that, alpha, my calculator is going to assume that I'm dealing with a standard normal distribution, and it's going to know the mean is 0 and the standard deviation is 1. In 6.3, we weren't dealing with standard normal distributions, and that's when we had to include the mu and the sigma inside the parentheses, whether we were using normal CDF or inverse norm. In section 6.5, the central limit theorem told us how we had to adjust the standard deviation when we were finding probability of an outcome for a group rather than an individual. Instead of saying find the probability that an individual man weighs, say, less than 180 pounds, I may have said find the probability that the mean for a group of 70 men was less than 150 pounds. When I'm talking about a group instead of an individual, that's when I have to adjust the standard deviation, and I adjust it by dividing it by the square root of the sample size. So the example that I just made up, a group of 70 men, what's the probability that a group of 70 men have a mean weight less than 150? I would still use normal CDF, negative 9999 up to 150, and I'd have the mean and I'd have the standard deviation. But because I'm talking about a group of 70 instead of just an individual, I would have to divide that sigma by the square root of 70, the square root of the sample size. And that's all we did in chapter 6, either normal CDF to get an area or inverse norm to find a score. Pay attention to whether or not you need to adjust the standard deviation.